Hello everyone. Welcome back to the channel. In today's video, we'll dive into one of the most fundamental concepts in strength of materials, the stress-strain diagram. Understanding this diagram is key to analyzing material behavior under load, which is essential for engineers and designers. So, let's get started. Before we talk about the diagram, let's quickly understand what stress and strain are. Stress is the internal resistance offered by a material per unit area when subjected to a load. It's measured in pascals or newtons per square meter. Formula: stress equals force by area. Strain, on the other hand, is the deformation or elongation of a material per unit length due to the applied stress. It's a dimensionless quantity, as it's a ratio of lengths. Formula: strain equals change in length by original length. Now that we know these basics, let's look at how materials behave under stress. The stress-strain diagram is a graphical representation of a material's behavior when subjected to tension. The x-axis represents strain, and the y-axis represents stress. Imagine you're stretching a metal rod. Initially, it behaves differently as the force increases, and the stress-strain diagram shows these distinct phases. Let's break it down phase by phase. Phase 1. Proportional limit. The first part of the curve is a straight line. This region is called the proportional limit. Here, stress is directly proportional to strain, meaning the material obeys Hooke's law, where E is the Young's modulus, a constant that measures the material's stiffness. If you remove the load in this region, the material will return to its original shape. This is known as elastic deformation. Phase 2. Elastic limit. Beyond the proportional limit lies the elastic limit. The material still behaves elastically, meaning it can return to its original shape after removing the load. However, this is the maximum stress the material can handle without undergoing permanent deformation. Phase 3. Yield point. Next comes the yield point. This is where the material starts to deform permanently, even if the load is removed. The stress at this point is called yield strength. In the diagram, this region may show a small dip before rising again, which is called the upper yield point and lower yield point. Phase 4. Ultimate tensile strength. At the peak of the curve, we reach the ultimate tensile strength, UTS. This is the maximum stress a material can withstand. Beyond this point, the material begins to weaken and necking occurs, where the cross-sectional area reduces significantly. Phase 5. Fracture point. Finally, the material reaches its fracture point. This is where it breaks apart completely. The distance between the origin and this point on the strain axis indicates how ductile the material is. For brittle materials, this distance is small, while ductile materials show significant elongation. Diagram comparison for materials. Different materials have unique stress-strain diagrams. For example, ductile materials like steel show all the phases we just discussed. Brittle materials like cast iron or glass break without showing much plastic deformation. Elastomers, like rubber, have a nonlinear elastic region with large strain values. Importance of stress-strain diagram. So why is this diagram important? It helps us determine a material's strength, ductility, toughness, and stiffness. Engineers use it to select the right material for a specific application, ensuring safety and cost efficiency. And that's a wrap on the stress-strain diagram. I hope this explanation helps you understand how materials behave under stress. If you found this video helpful, don't forget to like, share, and subscribe to the channel for more engineering content. Let me know in the comments if there's a topic you'd like me to cover next. Thanks for watching, and I'll see you in the next video.